Have you ever wondered what makes an airplane fly? There are four forces acting on an airplane in flight. These forces are lift, weight, thrust, and drag. The study of these forces and their role in flight is known as aerodynamics. Let's take a look at how these forces work together to achieve straight and level, unaccelerated flight. This means that the airplane is not turning, climbing, descending, or changing airspeed. It should be fairly clear that before an airplane can fly, lift must be created. Lift is the upward force created by the effective airflow as it passes over and under the wing. Weight is the force that opposes lift and is caused by the downward pull of gravity. Thrust, created by the power plant, propels the airplane forward through the air, while drag, a retarding force, opposes thrust and limits the speed of the airplane. In unaccelerated flight, where thrust and drag are equal, the airplane will not speed up or slow down. Like thrust and drag, when lift and weight are equal, the airplane will not climb or descend. To help you understand lift, let's take a look at the basic principles of motion. In the 18th century, Daniel Bernoulli expanded on Sir Isaac Newton's laws of force and motion to describe the principle of airflow pressure differential. Observing what happened to air as it passed through a tube, Bernoulli discovered that as the velocity of a fluid or gas increases, its pressure decreases. He also found that with a constant velocity, the pressure of the air remains the same at both ends of the tube. If a constriction is placed in the middle of the tube, the same amount of air has to pass through a smaller area. This increases the velocity and decreases the pressure. If you were to replace the constriction with an airfoil, such as a wing, the same principle would still apply. As oncoming air meets the leading edge of the airfoil, it separates with part of the airflow going over the top and part going below. Since the air flowing over the top has farther to go, it must travel faster. The result is lower air pressure above the wing. This is a component of total lift. The remaining lift is provided by the downward-backward flow of air generated from the top surface of the wing. The lift provided by this flow can be explained by Newton's third law of motion, which states that for every action, there is an equal and opposite reaction. The reaction to this downwash results in an upward force on the wing and an increase in total lift. Before we look at various airfoils and how they are configured to take advantage of the laws of motion and principles of lift, let's look at some of the terminology. A line drawn from the leading edge to the trailing edge of an airfoil is referred to as the chord line. The camber of an airfoil is the curve of its surface. On general aviation training aircraft, the upper camber is usually more pronounced than the lower camber. Any object moving through the air encounters a relative wind. This wind is always parallel to and opposite the flight path. The angle formed between the relative wind and the chord line is called the angle of attack. A way to measure lift as it relates to angle of attack is the mathematical expression coefficient of lift, or CL, which is determined by wind tunnel tests and is based on the design of the airfoil. Each airplane has an angle of attack where maximum lift occurs. This point is known as CL max. Beyond this point, the airflow begins to separate from the wing surface, becoming so turbulent that the airfoil can no longer create lift. At this point, the wing is in a stalled condition. The amount of lift that a wing can produce depends on several factors. One of these factors is wing design, which includes the shape or plan form of the wing. A straight wing has good slow flight characteristics, but is not structurally efficient in terms of lift and drag. A swept back or delta wing is much better at higher speeds. The tapered wing, on the other hand, has good slow flight characteristics and has a relatively efficient design. Another wing design factor is the aspect ratio, or the relationship between the wing's length and width. The aspect ratio can be found by dividing the wingspan by the average chord. In this example, the wing has an aspect ratio of 9. At a given angle of attack, the larger the aspect ratio, the less drag produced for the same amount of lift. General aviation training aircraft, for instance, normally have aspect ratios of 7 to 9, while gliders are usually between 20 and 30. Another design factor that affects a wing's flight characteristics is the angle of incidence. In this case, the wing is attached to the fuselage with the chord line inclined upward at a slight angle. You, as a pilot, can control lift by changing individually or in combination the airplane's airspeed, its angle of attack, and the wing configuration, such as lowering the flaps. If all other factors remain constant, doubling an airplane's airspeed develops 4 times more lift. This increase, however, is not without its drawbacks, since any increase in lift also results in an increase in drag. In addition, with all other factors remaining constant, an increase in angle of attack increases lift. For lift to remain constant, airspeed and angle of attack must be used in conjunction with each other. If airspeed increases, you must decrease angle of attack. Conversely, if you want to maintain the same amount of lift at a slower airspeed, you must increase the angle of attack. Another way of controlling lift is by changing the configuration of the wing. Lowering the flaps can increase the lifting efficiency of the wing and decrease the airspeed at which the airplane stalls. As flaps extend, they change both the camber and the chord line of the wing in the area of the flaps. This not only produces lower pressure above the wing due to the change of camber, but it also changes the wing's angle of attack. Suppose that with the flaps up, the angle of attack is 5 degrees. By lowering the flaps, which changes the chord line, the angle of attack increases to 10 degrees. This higher angle of attack provides more lift and more drag. Weight, like lift, is not a constant. It varies with the equipment installed in the airplane, the number of passengers, the amount of cargo, and the fuel load. During the course of a flight, the total weight of the airplane will decrease as fuel is consumed. In some specialized flight operations, such as crop dusting, firefighting, or skydiving, an additional reduction of total weight will occur. The forward-acting force which opposes drag and propels the airplane is thrust. The same physical principles involved in the generation of lift apply when describing the force of thrust. The thrust necessary to overcome drag and propel the airplane through the air is produced by the power plant turning the propeller. If you look closely at a propeller, you will notice that it looks like a twisted airfoil. As the propeller turns, a lower pressure area is created in front of each rotating blade. The low pressure in front of the propeller, like that above the wing, provides lift which acts forward. This forward-acting lift, or thrust, moves the airplane forward. During unaccelerated flight, where the airplane is neither increasing nor decreasing in airspeed, thrust and drag are equal. However, thrust may be increased by using the throttle to increase power. When you increase power, thrust will exceed drag, causing the airplane to accelerate. With this acceleration, however, there is a corresponding increase in drag. Drag will continue to increase until it is equal to thrust. When these two forces are in equilibrium, the airplane will stop accelerating and maintain the new higher airspeed. The force acting in the opposite direction to thrust is drag. There are two types of drag: parasite and induced. Parasite drag includes all the drag not directly related to the production of lift. It is generated by those areas of the airplane which disrupt the otherwise streamlined flow of air. These include items protruding into the airflow, such as the landing gear, rough surfaces, and the mixing of the air, such as where the wing joins the fuselage. As the speed of an airplane increases, the effects of parasite drag also increase. In contrast, induced drag is a direct byproduct of lift. It is greatest at slow speeds with a high angle of attack. Conversely, at higher speeds and at lower angles of attack, induced drag decreases. If the two drag curves are combined and the values added together, we can find a point where drag is at a minimum. This point is known as L over D max, which is where lift, when compared to drag, is at its greatest. In later sections, you will see that flying the airplane at this speed provides the best glide ratio and other performance benefits. The phenomenon known as ground effect occurs when the Earth's surface interferes with normal airflow patterns, thus causing a reduction in induced drag. During flight at altitudes, the downwash created by wingtip vortices causes the average relative wind to be inclined downward. Because lift acts perpendicular to the average relative wind, total lift is inclined aft by the same amount. The component of lift acting in a rearward direction is induced drag. As your airplane descends to within one wingspan of the ground, the wingtip vortices and resulting downwash are deflected horizontally. This in turn moves the average relative wind closer to the horizontal and the total lift vector closer to vertical, thus increasing the vertical component of lift and decreasing induced drag. As a result, the airplane tends to fly longer in ground effect or float down the runway. This can be a problem on shorter runways. Another problem occurs during takeoff, where you may lift off in ground effect at a very slow airspeed. If your airplane hasn't accelerated to a safe climb speed before climbing out of ground effect, the airplane could settle back to the runway. The information presented in this section has provided you with a fundamental knowledge of the forces at work on the airplane during straight and level, unaccelerated flight. The next section will expand your knowledge of what happens to the four basic forces during maneuvering flight.